Let us discuss about the excess pressure inside a liquid drop. We know that due to the forces of the surface tension or due to the surface tension, the free surface of a liquid tends to have the minimum possible area. And for a given volume, the sphere has got the minimum area, so the liquid drops at a rest or in equilibrium or of spherical shape. But we know that the surface tension or the forces due to the surface tension want to decrease the area of the drop, but the area of the drop doesn't decrease to zero. That means there is pressure inside the drop that is pushing the drop outwards. In another way, that means the inside pressure of the drop is more than the outside vapor pressure, and that difference is called as the excess pressure. Let P0 be the atmospheric pressure and Pi be the inside pressure of the liquid drop. So we can have the excess pressure as Pi minus P0, where Pi is the pressure inside the liquid drop and P0 is the atmospheric pressure. That means when the value of the inside pressure is more, the atmospheric pressure is not able to crush that drop into zero surface area. Now let us consider, due to this excess pressure, there be a small increase in the radius of the drop. So the new shape of the drop is shown by the dotted lines. Now the work done by the excess pressure is equal to force into displacement. The force is pressure into area. The excess pressure is P and the area of the drop initially is 4 pi r square, as r is the radius of the drop, and the displacement is equal to delta r, that is increase in the radius. Let us see what is the increase in area. Increase in area is final area minus initial area. The final area is 4 pi r plus delta r whole square minus 4 pi r square. As there is increase in the radius by an amount of delta r, so the new radius is r plus delta r, so the new area 4 pi r plus delta r square minus the initial area is 4 pi r square. So the increased area is the final quantity minus the initial quantity, and that equals to, if we take 4 pi common and solve this is a plus b whole square, that is a square plus b square plus 2ab, 2r into delta r minus r square. This r square and r square goes, as the change in the radius is very less, so this quantity delta r square is very less, so we can neglect this quantity. So we can have the increase in area, that is delta a is 4 pi into 2r delta r, and that is equal to 8 pi r delta r. 8 pi r delta r is the change in area due to that excess pressure. As the area has been changed, that means there is an increase in the surface energy. So the surface energy is equal to surface energy E is equal to change in area into surface tension, that is 8 pi r delta r into S, where S is the surface tension. As the liquid drop is in equilibrium, change in surface energy is due to the work done by the excess pressure. So we can equate this equation and this equation, that is W is equal to E. The work done by the excess pressure is changed into the surface energy as the surface area of the drop is increased. As the drop is in equilibrium, these two quantities equate. We can say that 8 pi r delta r into S is equal to P into 4 pi r square into delta r. Cancelling this delta r and delta r, 1r and 1r, pi and pi, equating this 4 into 1, 4 into 2, we have got 2S is equal to P into R. We have got the equation for the excess pressure, that is P is equal to 2S divided by R, where 2 is a constant and S is the surface tension and R is the radius of the liquid drops.